All right, welcome back. So yesterday, our last class, we initiated our discussion of the first law of thermodynamics. And the main takeaway is that thermodynamics seems very silly and contrived because it is very silly and contrived. What we're going to do now is go over the history of the first law and build a parallel timeline between the first law of thermodynamics and the development of atomic theory that really hopefully drives home the point. The approach we took yesterday was to highlight a degrees of freedom approach to thermodynamics. So 1, we had the first law of thermodynamics. 2, we had the second law of thermodynamics. 3, we have an equation of state. 4, we have the definition of temperature, which I don't want to put out on the top of my, actually I can. So 1 over T d S d U and constant B. And the definition of pressure from a macroscopic system, which is the relationship between internal energy and fluid density at a constant entropy. You'll note these two equations here are not ones that you would necessarily want to solve in, let's say, any math class. They're not in a form that we can actually use because we don't have an explicit equation for the entropy of a fluid. So there is no way that we can substitute in an equation for the entropy of a fluid and then simply integrate it with respect to the variable U. Now, one thing that we can do later on in the future that we'll talk about with statistical mechanics is we will actually be able to develop theories for entropy using things like lattice-based models. So if you have a grid, 2-dimensional or 3-dimensional, and you say that atoms can only be on grid locations and grid positions, then we can start to explore how entropy may exist in a macroscopic form. But from a classical thermodynamic perspective, these equations are actually intractable to solve. The variables that we would like to know are the internal energy, the entropy, the temperature, the pressure, and the density. Sorry, I was taking a second to remember that last one. So from a degrees of freedom perspective, we have thermodynamics fully defined and understood. The challenge here is that none of these relationships are trivial to solve. So instead, what we'll do eventually is in our degrees of freedom approach, we're not going to rely on these approaches here, but rather we will define new variables that are helpful. Specifically, heat capacity, and heat capacity in basically 2 different forms. T and constant heat. Now we can't actually get access to these properties from foundational principles of thermodynamics. But we've recognized that if we measure those experimentally in the laboratory, they're extremely powerful and valuable tools. Now, so if we forget about this one here, for example, right? If we introduce C sub V, we're introducing a new source of information that relates between some of the key variables of our system. Again, thermodynamics, as I like to think about it, is the system that we're going to go through here. So that's a quick refresher of what we started on the principles of thermo. So in this class, we are starting here. Nothing that will be put on this chalkboard is not going to be derived from these terms. Everything is going to be a manipulation of the first law, the second law, and along the way, we're going to be defining new terms. Enthalpy, heat capacity, Gibbs free energy, isothermal compressibility, blah, blah, blah. These are all relationships that must be experimentally measured in order for us to calculate the thermodynamic properties of interest, specifically energy and entropy, to make sure that we satisfy the first and second laws, and then temperature, pressure, and volume because those are the valves and nozzles that we can control in an actual chemical process and in the laboratory. I don't have a machine where I can go up to it and say, control the entropy, control the enthalpy, right? I only can control the temperature, pressure, and volume. If I want to control the internal energy, then whatever device I'm using is doing some calculations in the back based on these principles here. So everything will be built up from this more or less degrees of freedom approach to thermodynamics. So one area that's often overlooked in thermo that I think is a critical component is the notion, effectively, the Gibbs phase rule, that if I know two variables of a pure fluid, that means I can use a relationship to calculate the third. So without that notion, our degrees of freedom approach falls apart. So with that, if I have the first and second laws and then an equation of state, the Gibbs phase rule gives me the power to then manipulate it and know that I can solve for the other remaining properties. So one of the key things to walk away from this course, if nothing else, is that all of the world is described and all the universe is described by only three properties of matter. But those three properties of matter are very much hidden within abstract and complex terms. For example, entropy, everyone's favorite variable. Okay, so the motivation for the study of thermodynamics more or less coincides with the Industrial Revolution. The objective in a chemical engineering perspective is we want to modify processes. We are going to have a stream that comes into some magical box that is doing some action. This could be the human body, this could be a chemical plant, this could be a pot of water on your stove that you're boiling to make pasta or rice. Whatever the case is, this is some sort of a process. And we want to know the relationship between the inlet and the outlet stream. And we want to know how much heat or how much work am I going to put into this system. So when statistical mechanics was derived in the late 1800s, the real power of it is that it was able to more accurately predict the properties of superheated and high pressure steam. And as we'll talk about in a little bit, those ideas were at least initially first rejected. They loved the ability to predict the properties of steam, but overall they didn't believe that the formulation of atomic theory was actually correct. So this is the foundation of where we're getting to here. So the foundational principle, I would say, or one of the ones to knock off, is we'll focus first on more or less this term here. Kind of this term. Maybe I'm trying to draw too many connections. But back in 1774, Anton Lavoisier performed experiments to determine the law of conservation of mass. How this was performed is that he took pure solid carbon in the form of diamond, used focused light, mixed it with oxygen in the appropriate stoichiometric ratios. Right? People could separate atoms back then and they knew what different elements were, but they didn't know how the matter was assembled in the inside. Burnt it completely to carbon dioxide, and the mass was constant. And thus was born the law of conservation of mass. And since we are not going to be dealing with any sort of nuclear processes, the law of conservation of mass is not going to be broken in any way. Now, from our perspective, we typically will write the law of conservation of mass in the form of a mass balance. Specifically, all we are going to do is keep track of the rate of flow of all of the mass into the system, subtract out the rate of flow of all the mass out of the system. If these two terms are imbalanced, we will have an accumulation of mass in the system. So for example, if I'm pouring water into a bucket, Hopefully it's not leaky. And the rate of change of mass in the bucket is going to be equal to the rate that I'm pouring it into the system. If there is a small leak, then you can have a loss term. This is the differential form of a balance. And for the mass balance, I'll also write out the integral form of the balance, but we'll basically not really use that one, at least explicitly. We'll kind of use it implicitly. So you can also think of this as the mass at time 2 minus the mass of the system at time 1 is going to be equal to, and it's sort of silly because I'm just integrating the above expression, right? Since mass is a state variable, if I have a kilogram of water, it doesn't matter how I got there. I could scoop a kilogram of water out of a lake, or I could pour a kilogram of water into a bucket. A kilogram is a kilogram is a kilogram. So the nice thing about thermodynamic math is if I just go like this to a state function, I don't care how we got there. So I magically transform this ordinary differential equation into mass 2 minus mass 1. Right? It's very nice to do thermomath. You'll feel like an all-star when you do thermomath. But all we're doing then is just integrating that expression. This is the integral form. So we can look at the rate of change, or we can look at the total amount that has changed over the course of time. All I've done is add an integral to this expression. Okay, so I'll call this number 1 in the foundation. Number 2 in the foundation is the law of conservation of energy. Now this was first formulated in 1638 by Galileo. And he was specifically looking at the transition between potential energy to kinetic energy. The first approach he took was to have a curved surface and basically had a ball roll up and down that surface. However, there was too much friction involved. So let me just double check the video here. My screen went black, but I think we're still recording. Yep, still recording, good. But then it was determined that that was too much friction, so instead he switched to a weight on a pendulum as it swung back and forth. And this is old hat to us now. But at this position here, the pendulum had swung up all of the way to its maximum. It had no kinetic energy. So that means that the total energy of the system was constant. So if I were to plot the potential energy, in this case gravitational, gravitational potential energy as a function of time, it would be some sort of a sinusoidal curve like so. This is the potential energy of the system. And then the kinetic energy is 0 when there's no velocity. It's maximum when it's at its highest velocity and no potential energy. And then it goes back down. But the total energy of the system is conserved. So this is a very well-established concept, right? You cannot create or destroy energy. 1800s, to me at least, is a very long time ago. But what about heat? What about work? What is the relationship between these different forms of energy for heat and for work? So the third sort of foundational principle of thermodynamics from a historical perspective, well, I guess, and then the second law would be what we'll talk about next class, is going to be the development of the first law of thermodynamics. Now, early theories, and one that's nice to talk about is caloric theory. Caloric theory is actually the approach that Carnot used to derive the Carnot cycle efficiency. The idea of caloric is that it was a weightless gas that carried heat. So cold meant the lack of caloric. The assumption and the approach was that caloric was conserved. Meaning that you could not create or destroy caloric. You could only transition heat from one body into another body. And this makes a reasonable amount of sense, because if I took a cold object and a hot object and I put them together, then the heat would transfer from the hot to the cold, and the approach worked actually reasonably well if you had an isolated system, right? There would be an energy conservation for an isolated system because there's no external work or heat input on the process. In 1798, an individual named Count Rumford performed the first experiments to dispute caloric theory. How this was done is he worked in a cannon manufacturing facility. I believe, I don't know in 1781 if this was Prussia or Germany, but modern day Germany, specifically Munich. And how they would build the cannons is that they would have a cannon tube, whatever you want to call it, immersed in water to cool it down, and then they had a borer that would go on the inside and cut out and smooth and make it so that the cannon was, of uniform shape, so that it could, be really a good cannon or something. What he found was that he could boil the water in this tank in 2.5 hours, but that the longer he bored out the cannon, it would continue to boil the water. And thus, he was putting work into the system, and the fluid was continuously heating up. In other words, according to Count Rumford's experiments, caloric theory could not be correct because heat could be infinitely created using, the transition of work into heat energy. Now, the downside was that no one really believed the experiments. If you went to your advisor and tried to disprove a well-known thermodynamic theory with a cannon experiment, you may have similar skepticism as well. However, the experiments were expanded upon by a well-known individual, James Prescott Joule. So, in the mid-1800s, James Prescott Joule, and this is approximately 1840, it was a series of experiments. He verified Count Rumford's work by a couple of approaches to all highlight that energy in the form of heat was the same as the energy stored in the form of work, was the same as the form of energy stored in the form of electricity. So he demonstrated basically the first law of thermodynamics by a number of ways. First was viscous heating of water. So he had a narrow channel, and basically by knowing how much weight he pushed on one side versus the other, rocked the water back and forth through a narrow channel. So we had an opening, a narrow channel, going to another opening, and then just slosh that water back and forth through many, many times over again. And what they found is that he was converting mechanical energy into temperature by forcing that fluid and causing it to heat up by the viscous dissipation forces of that water itself. He also heated water with electricity. He also looked at PV compression of gases. And in all instances, he developed the relationships between mechanical, electrical, and heat energy. And that's why Joule is not a household name, I would say, but it's a well-known name for everyone in chemical engineering. So this was the final nail in the coffin for caloric theory in the 1800s, which we're getting relatively modern in times, but that's certainly well after the Industrial Revolution. Now, this is a really nice piece of information, particularly for new PhD students and, let's say, future PhD students, for all the master's students in here. This paper was rejected by the Royal Society. So one of the best known scientists from the 1800s could not get his research published. So don't beat yourself up if you have some struggles early on getting your work recognized. All right. And that basically brings us to the thermodynamics of modern day, save for the second law, which we'll talk about in greater detail. But now it is a very useful exercise to contrast this. So I deleted this slide right here. I erased it, using computers too much. 1700s for the law of conservation of mass, 1600s for the law of conservation of energy, 1800s for the first law of thermodynamics. Second law of thermodynamics, just for a little teaser for next class, was actually late 1800s, early 1900s, and even up until the modern day are people still trying to find better formulations of the second law of thermodynamics. Particularly, how do you define the second law without invoking the concept of temperature, without invoking the concept of pressure, without invoking the concept of work? So the second law is a little playground for mathematicians and physicists to this day. All right, the history of atomic theory. Because when you walk into your first year, first semester thermodynamics class, they tell you, oh, internal energy, that's the kinetic energy of molecules, that's the bond energy of molecules, that's the vibrational energy of molecules, that's the rotational energy of molecules. So forget all of that, and we'll lump it all into this term U. Right? But the reality is actually flipped. U came first, atoms came second. So those who developed atomic theory had to justify their predictions with the existing approach of thermodynamics. Same thing with statistical mechanics, same thing with quantum mechanics. Thermodynamics has still never been defeated, right? And I've heard it attributed to Einstein, but I don't know if it's actually attributed to Einstein, right? They state that the second law of thermodynamics is the most perfect law in all of physics. Basically, that it's very simple. It's really just ds is greater than or equal to 0, and it's never been disproven. So in atomic theory, the advent of atomic theory comes from John Dalton. Now this is neglecting sort of the suppositions of the ancient Greeks, right, where they got the name atom from. But they had no actual evidence of this. Now John Dalton lived from 1776 to 1844. He was an English, I guess we would say, chemist in this day and age. What he found was that elements were often found in the same ratio. Right? So for example, if you split water, you would always get 1 H2 and 1/2 O2. They didn't know what made up hydrogen, they didn't know what made up water, but they knew the ratios were consistent. Same thing with benzene. They knew it always had the same amount of carbon, and they always knew it had the same amount of hydrogen as well. So what he presumed was that the world was made up of very small, indivisible particles that would support this type of a behavior. That if you split a fluid into its constitutive elements, that it would always be in the same ratios. So his presumption was that there was probably some indivisible small particle that made up the matter itself, which we all come to accept now. The next big leap in atomic theory comes from a combination of Maxwell, James Clerk Maxwell, and Ludwig Boltzmann. So I'll just focus on Boltzmann here. Boltzmann lived from 1844 to 1906. He was an Austrian physicist. His contribution was the kinetic theory of gases. Right, so essentially what he and Maxwell derived is the velocity distribution of gases at a given temperature. So what this approach did, so for example, this is the Boltzmann distribution. So if you had some number density as a function of kinetic energy or the velocity of the particles, right, you have some distribution of those energies. And this is the famous Maxwell-Boltzmann distribution. Right? It's the ideal gas distribution of kinetic energies of particles. So what kinetic theory of gases did, it gave meaning to temperature and pressure, such that temperature, as we know it now, is the average kinetic energy of gas particles, and pressure is the force of the collision of those gas particles with the surface. Classically, there was no good definition of what temperature and pressure were. Now, the proportionality relationship between temperature and kinetic energy is which property? I think we talked about this on Monday. What is the proportionality relationship between temperature and kinetic energy for particles? It's named after this gentleman.
Yeah, you're talking about the value?
Yes. A property, like a physical constant of sort of the universe. It is the blank constant, Boltzmann constant. The Boltzmann constant, which was shown to match the data of the properties of fluids, calculated by Boltzmann, was 1.38 times 10 to the minus 23 joules per Kelvin. A simple proportionality relationship between the temperature of a system and the kinetic energy of the system. Now, you may know the Boltzmann constant better in a different form. The ideal gas constant, which is, oh my gosh, it's been too long since I've been doing this. 8.314, I don't know how I ever forgot that. Joules per mole Kelvin. This is simply Avogadro's number multiplied by the Boltzmann constant. Prior to teaching this class thoroughly, over many years, I could never remember what the Boltzmann constant was. So all I did was take 8.314 and divide it by Avogadro's constant, 6.022 times 10 to the 23. So here's the problem, though, with Boltzmann's approach. Well, there's no actual real problem. Here's the perceived problem by scientists of his era. This number is very, 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 very small. Right? Back in the 1800s with Galileo, they sort of already knew what kinetic energy was. And scientists had very certainly determined it was 1/2 mass velocity squared. So in order for this proportionality relationship to be true, you can calculate the kinetic energy of a particle, right? And that meant that the atom had to be so inconceivably small that there was no point in ever worrying about it. At least back in in the early 1800s. So this theory was developed in 1871. Let me put that here. In 1871, we didn't have scanning tunneling microscopes. We didn't have X-ray scattering. We didn't have neutron scattering. We didn't even know if an atom was a real thing or not. Boltzmann was the first to basically provide a theory and a foundation for how the concept of an atom could be integrated into science. So subsequently, no one paid attention and no one listened. So they thought that what Boltzmann had done was essentially very clever mathematics, and that the concept of an atom was simply a mathematical construct that allowed for an easy calculation that was relatively accurate. So unfortunately, in 1906, Boltzmann committed suicide, in part because he was rejected by the scientific community for his ideas. However, another sort of research lesson hidden within here, if he had been reading the literature more closely, in 1905, an individual whose name we all recognize, Albert Einstein proved Boltzmann's theory correct. And he did it in his development of the theory of Brownian motion. So Brownian motion is the process by which, if you look under the microscope, and this is originally done with pollen particles that are very, very small, but nowadays we do it with colloidal particles like silica, on the order of a micron in size. Very small statistical fluctuations in the local kinetic energy of a fluid, described by Maxwell-Boltzmann's kinetic energy distribution, will cause this particle's center of mass to jiggle and move around. Now, this random walk motion is the source of diffusion. It's how energy is transferred in the form of conduction. It's how diffusion occurs. Now, Brownian motion is the theory by which you can predict the diffusivity of large particles whose movement is caused by the statistical fluctuations of temperature within that fluid itself, thus validating Boltzmann's statistical mechanics and validating atomic theory. Further, in 1908, I believe this is a French individual, Jean Perrin, he measured Avogadro's number with Brownian motion. Thus confirming these relationships right here between the gas constant, which could be measured macroscopically. I don't remember what they're called, like is it Boyle's law and someone else's law that you learned in chemistry class? That you can validate the gas constant with Avogadro's number to confirm Boltzmann's calculations for effectively the size of what an atom would need to be in order for those theories to be correct. All right. So, we are at 1905. Now, to me, that seems very recent, at least in the terms of scientific discoveries. In 1905, we finally had the scientific community accept the concept of an atom. 1840, almost 60 or over 60 years ago in the past, that's when the first law of thermodynamics was developed. So they had been building a lot of ships and a lot of factories in the meantime. So if I'm a businessman in the early 1900s, I'm not going to adopt atomic theory unless it can predict the theories that have already been used in order to give me lots of money and productivity from burning steam and all that, or burning coal and all that other stuff. So we're going to wrap up by talking about atomic structure. And then hopefully we all realize how much knowledge we walk into a typical thermodynamics class with, right? Because at this stage right now, all that we've done is we've defined that matter is made up of very small particles called atoms. In 1889, sort of coinciding with sort of similar developments, J.J. Thomson discovers the electron. So this was done by using a cathode ray tube to deflect a beam of electrons. And what this established was what we call the plum pudding model. Wherein matter was considered to be sort of a goo with positive and negative charges distributed throughout. Again, not really reliant on the concept of an atom. 1911 brings us to, I believe, a British individual, Ernest Rutherford, performed the famous gold foil experiments. In which they used a radioactively decaying substance to produce alpha particles, which is basically just helium stripped of its electrons, through a very thin gold foil. Most of these, actually no, they wouldn't be waves, they'd be particles. Sorry, let me redraw that. Most all of these continued to go through completely unobstructed. Now there was a very small amount of these that got scattered and deflected. And Rutherford actually recognized this and out of a curiosity gave the task to his poor graduate student to take this photodetector and move it and take a long series of images. And with this information, they were actually able to calculate what we call the cross-section of a molecule or a nucleus. So what this found is that since most of the alpha particles went through completely unobstructed, the conclusion was that atoms are mostly empty space, and that by measuring the very, very faint scattering events or deflections, you could actually calculate classically how large the cross-section of a nucleus was. Now, of course, at that length scale, right, particles behave very much like waves. So this concept of a cross-section, sort of the idea if I shine a flashlight on my paper, right, that is casting a shadow. That's kind of the cross-section that obstructs the light. It's a classical analogy to a non-classical process. But that's what we typically use. So what they found is that this developed the Rutherford-Bohr model. Rutherford-Bohr model, in which case you had a very small localized positive charge surrounded by negative charges. But again, 1911 is before the advent of quantum mechanics. Then from, let's see, the 1920s onward, there are a number of physicists that can be credited with the development of quantum mechanics. And I won't go into the excruciating details of quantum mechanics because at this point, for classical thermodynamics, this is not particularly relevant. When we start to talk about statistical mechanics, then we can invoke a little bit more quantum mechanics. So, the first law was developed over the period from about the 1600s to maybe 1840, where Joule kind of put the final nail in the coffin against caloric theory. The second law of thermodynamics was formulated from about 1850, we'll talk about this in the next class, to approximately 1910 is where it more or less got fairly solidified in a mathematical construct. But again, we're still tinkering around with the second law of thermodynamics to this day. Atomic theory was established between about the 1870s to 1920 plus, and we're still, of course, tinkering around with our understanding of that process. So you'll notice here that atomic theory came absolutely last. So like I said before, everything had to coincide with all of it. Just as an additional point of reference, because I think this is sort of a neat piece of information, the van der Waals equation of state, which is the standard equation of state that everyone uses to teach how phase transitions occur. It's the simplest equation of state that actually predicts the existence of a liquid, right? So the ideal gas law, if I compress my system and I compress my system, all that happens is the pressure shoots up to infinity. It'll never condense to a liquid. So the ideal gas law does not predict that a liquid exists. The van der Waals equation of state is the first to ever do so, and this was developed in 1873, sort of without the necessary insight into atomic theory. So van der Waals, this was his PhD dissertation. And he was awarded the Nobel Prize for his PhD dissertation in 1910. So he got the Nobel Prize for physics for his PhD dissertation, which is, I would say, quite a substantial accomplishment. Okay. Let's see, I think I covered a lot of this over here. So what we will do in the last little bit of class is jump us into the modern era of how we now apply all of these concepts. So are there any questions? And also remind me if you ask a question if I don't repeat it for the audio so that it's clear for the videos in the future. Any questions? So this is, I guess, a history lesson. All right, so I want to talk about the energy balance in the form that we all will see as chemical engineers, and it's going to be really the starting point for anything that we work on in terms of that. Specifically, I want to highlight why we use the enthalpy in energy balances, and then let's also introduce the form of the energy balance that the chemical engineers will use. So the question here is, why are we including PV in the definition of enthalpy? Does anyone know why? Does anyone want to venture a guess? Yes, Ruben.
Is as an expansion?
That is true. It's very useful for constant pressure systems. But there's another really good use for it as well. So in a constant pressure system, the rate of change of the internal energy as a function of time for any particular process is going to be the rate of heat input plus the rate of work input. Now we can rewrite work as minus P dV dt. So if I move this over to the left-hand side of the equation, I get d dt, actually I think this can be total differential, of u plus p v equals q dot, and thus we have dH dt is equal to q dot for a constant pressure closed system. I know it's closed because in my energy balance, that I'll talk about in a moment, I have no energy input in the form of matter. Right? Matter brings with it energy in the form of kinetic energy, chemical energy, vibrational energy, and so on and so forth. But for open systems, this is where enthalpy really shines. So I have my chemical engineering process here, and I am flowing some material into the box, and there is some material flowing out of the box. Now, due to more or less inertia, fluids don't want to move unless they want to move, which is really just a restatement of the law of conservation of energy. To get a fluid into the system, I have to pressurize the fluid to push it in. So if I'm filling up a balloon with air, I'm pressurizing the air in my lungs relative to the atmosphere, and I'm forcing that air to the balloon. There is going to be some volume or density of that fluid that I'm trying to push into the system. Actually, let me do this a little bit differently. Every time I deviate from my notes, I always make a mistake. And this is delta M1. So in this notation here, this is the notation of the Sandler book, which is, I think, quite good, but oftentimes it's criticized as being a little bit overly pedantic. The little hat on top of variables is going to be meters cubed per kilogram, as opposed to the little underbar, which is meters cubed per mole. So just to clarify the notation here. So in order to get this mass of fluid with density V, or specific volume V, I always use the terms interchangeably, sorry, I have to pressurize it to push it in. That's actually giving energy to the system, right? Because I'm giving a little bit of PV energy into the system. And likewise, leaving the process, I have a fluid with density 2, a delta mass of 2, and leaving at pressure 2. The system has to give a little bit of energy to this fluid to push it out of the process. So if I were to look at an energy balance, the work going into the system is pressure 1, density 1, mass 1. So if we look at the units of this really quickly, we'll do pressure in pascals. We will do the volume of the fluid in meters cubed per kilogram. Excuse me. And that the density is in units of kilograms. A pascal per meter cubed is what? What's that?
Specific volume.
No, so what if I multiply a pascal times my meter cubed? Excuse me.
Okay, nice work. That's joules.
It's joules, yes. So in the gas constant, 8.314 joules per mole Kelvin is exactly equal to pascals meter cubed per mole Kelvin. So P times V is a unit of energy. Right, so rate of work in here. Well, this is technically, let's say, energy in, not work in, sorry. The energy out is minus P2 V2 delta M2. So if I put it all together, what we get for the energy balance of this particular system, if we take, let's see here. So if we have the summation of all of the mass flow rates of a particular stream going into a system, we have internal energy, we have the PV contribution from here. We can also include kinetic energy. We can also include a potential energy term. Right, so this is the way that we're keeping track of all of the energy going into and going out of the system. So what we'll do is we just lump these together into one called the enthalpy. So the reason why we have enthalpy is because you have to do a little bit of work on the system to actually get fluids to flow into a particular process. Now for our class, for most everything that we're going to cover, we're going to ignore the kinetic energy or ignore the potential energy. The example I like to give, and normally I'd have a drink of coffee at some point, but if my coffee was tepid or cold, and I wanted to heat it up, would it be an effective strategy to throw it against a wall or drop it from the roof? How many times would I have to do that to get it to a hot temperature again? I'm assuming it's a very, very large number of times. So the sort of enthalpy and internal energy of a fluid is vastly higher than most any instances that we're going to see. So we'll close with the modern form of the energy balance, in which case all we're doing is being accountants for energy. I'm keeping track of the total energy of my system right here. If there's an accumulation, the rate of change is going to be something different than 0. If it's steady state and there's no change, this is going to be equal to 0. So what I write it as is the summation of the mass flow rate of species for stream, stream I, the enthalpy of that stream, plus the heat input plus the work input. This is the modern form that we work with as chemical engineers. For a closed system, there is no mass flow in or out, so this is going to be for open. And then for closed, du dt is equal to heat and work. But as was pointed out earlier, right, it's not as simple as just saying, oh, it's a closed system, you use delta U. Oh, it's an open system, you use delta H. Right, delta H can still appear in a constant pressure closed system. So if nothing else, all you should do, and for every exam that you work on that has a balance, you need to write this equation out because it's going to be the starting point for all the problems. All right, that wraps up the first law of thermodynamics. Friday, we will talk about the second law of thermodynamics. Have a great day.